Here is a picture of the n by n grid of integer points in the two-dimensional plane. And on top of this picture, I've drawn the curve y equals x. Okay, those are all the points. This line consists of all the points where the x coordinate and the y coordinate are equal. And you see that this line hits n points of this grid. Namely, it hits the points 1, 1, 2, 2, 3, 3, 4, 4, and so on. Okay. Now here's a picture of the curve y equals x squared. And this time you see that the curve hits fewer points of the grid. Because as soon as x is bigger than square root n, the curve exits the grid and it's not going to hit any more points. Okay, so it just hits the points 1, 1 squared, 2, 2 squared, 3, 3 squared, and so on. All right, so we can try to hit more points of the grid by taking a different parabola, maybe this one. Okay. So how many times do you think this curve hits the grid? Well, in this video, I'll prove to you that even this one hits the grid only square root n times, approximately. In fact, something more general is true. In general, if you take an equation of degree d, then the curve you get can hit the grid in at most n to the 1 over d points, more or less. Okay, so up to like some polylog factors, the number of points that the equation can hit is n to the 1 over d. Okay. So this is a really basic theorem. It answers a very basic question about just polynomials and hitting the grid. These are very basic objects that we hear about in mathematics, very early on. And that's why I think this result is amazing. One of the great joys of doing math is that even though I've been doing this for a very long time, a decade or two, there are still results, basic results that I learn about that I'm shocked by, and I've never heard of them before. And this is one of those results. I learned this result only a few weeks ago. And when I first heard about it, I thought, okay, this is really basic. There's got to be a really simple explanation for this kind of result. But in fact, the proof of this result is quite deep. It uses some deep concepts from algebraic geometry. And even after thinking about it for a little while, I wasn't able to come up with a simpler proof. Okay. And that's surprising to me. So here is a statement of the theorem that I'm going to prove. It says that if f of x is a polynomial of degree d, then there are at most this many integer points of the type x, f of x, in the n by n grid. Okay. So now this is maybe a formula that's a little bit hard to parse, but one consequence of this formula that's easy to check is that if log n is much bigger than d, then the number of points here looks like polylog n times n to the 1 over d. Okay, the upper bound is of scales like n to the 1 over d. In fact, the result is a little bit stronger. Let's write f to be the polynomial in two variables that looks like y minus g of x, where g of x is a univariate polynomial. Okay, univariate polynomial like this one. Then you see that this polynomial is irreducible, meaning that you cannot express f as a product of two other polynomials in two variables. And the stronger theorem says that if you have a non-zero irreducible polynomial f of two variables, a polynomial that cannot be factored into two other polynomials, then the number of points where f is 0 in the n by n grid is bounded by this formula. Okay, a formula that's very similar to what we had here. So that's the stronger result. And for most of this video, I'll actually prove a weaker theorem for a weaker case that actually proving this weaker case already involves most of the ideas that go into the proof of the strongest version of the theorem. So that's where I'll focus my attention on for most of the video, and then I'll return to proving the stronger theorem at the end. So what is a weaker theorem that I'll prove? I'll add an assumption which is necessary for the key ideas of the proof. So suppose I have a polynomial f of x of degree d, and I know that the derivative of f of x in the range x between 0 and n is bounded. Okay, so the magnitude of the derivative is bounded by 1. Then for such a f, I'll prove that the number of integer points of the type x of f of x in this interval is bounded by this expression. Okay. This is the same kind of expression we had here. All right, so those are the theorems that I'm going to prove, and most of the time I'll spend proving the weaker version of the theorem. I should point out that in the weaker version, I'm not just talking about the points x f of x in the n by n grid, but all integer points of the type x f of x. And the reason I can do that is because if you know that the derivative is bounded, then points of this type must lie in some n by n grid, because f has bounded derivative, so it can't go very far away from where it started. Okay. All right, so those are the theorems I'm going to prove, and before I go further, I want to say something about the proof that I find very appealing. So there's another reason why I really like these ideas, and that's that they involve a trick that I find to be extremely brilliant, and it shows up deep inside the proof, but I'm going to talk about it right away just to explain why I find the proof so appealing. So a key technical step of the proof involves doing something that we do in many proofs in mathematics and in theoretical computer science. So often we're in the situation where you have a bunch of points and we're trying to find a low degree polynomial that explains those points. Okay, so maybe a bunch of points in the plane, and we want a low degree polynomial that takes on the value 0 on all of those points. So that's a key step that shows up in many arguments. And often the easiest way to do that, and the most common way to do it, is do the following. Make a matrix, take a bunch of monomials, say typically like low degree monomials, and make a matrix where the ijth entry is the evaluation of the monomial, the jth monomial at the ith point. Then, if the parameters are set up so that the number of monomials exceeds the number of points, okay, then you know that the rank of this matrix must be less than the number of monomials. Okay, because if you have a matrix where the number of monomials is bigger than the number of points, then the rank of the matrix is less than the number of monomials. And therefore, there's some linear combination of the monomials that vanishes on all of the points. It's just a very simple argument. The rank of a matrix is bounded by the number of columns and the number of rows. Okay. So this is a very commonly used argument. In this proof, they're in a similar situation, but they do something, the proof does something very brilliant. During the proof, we'll encounter the same kind of situation, but we will not have that the number of monomials is bigger than the number of points. In fact, the number of points could be much bigger than the number of monomials. But we'll achieve the same thing. We'll find a polynomial that vanishes on all the points, and the way we'll do that is first we'll use to do that, we'll again prove that the rank of the matrix is less than the number of monomials. And how will we do that? We'll actually prove that every k by k minor of the matrix M has zero determinant. Okay, that would prove that the rank is less than the number of monomials. And the way we'll prove that it has zero determinant is we'll actually use the fact that these are integer points. In the proof, that these will be integer points. And that means the determinant of this minor must be an integer. And further, we'll be able to control the magnitude of the determinant. We'll be able to show that the magnitude of the determinant is less than 1. And if you have an integer whose magnitude is less than 1, then it must be the 0 integer. Okay, so this is really brilliant. So you can start with an estimate of a quantity, show that it's small, and if the estimate is small enough, less than 1, then you actually get that the quantity is 0 because you know it's an integer. And that allows you to go from estimates that have errors in them to getting a bona fide linear combination of the monomials that vanishes on all the points. Okay. So that's the heart, that occurs in the heart of the proof, and I think that's a really nice idea. Okay, so let me go back to, let me now continue to try and complete the proof. So here's the theorem we're going to prove for most of the video. So a key hammer that we'll use is a tool from algebraic geometry called Bezout's theorem. And I will use this repeatedly. So what Bezout's theorem says is that if f is irreducible and f does not divide some other polynomial g. So now f is a polynomial in 2 variables. So suppose I have an irreducible polynomial in 2 variables and it does not divide some other polynomial g. Then the number of common roots of f and g is bounded. And it's bounded by the product of the degrees of f and g. So given this tool, what will we do? Well, our goal will be to find a small number of polynomials, g1, g2 through gk, such that every integer point of the type x, f of x, occurs as a root of some gi. So we'll find a small list of polynomials that covers all of the integer roots of the type x, f of x. And moreover, the polynomial y minus f of x will not divide gi for any I. So we can apply Bezout's theorem. And so then Bezout's theorem will say that the number of integer points is bounded. It's bounded by the degree of y minus f of x times the sum of the degrees of all the gi's. And all of these gi's will also be of low degree, relatively low degree, but they'll be of degree roughly log n. Okay. So that's a high level structure. So we'll bound the number of integer points by covering all of them by with low degree polynomials that are relatively prime, that are not divisible by y minus f of x. Okay. So let me start to explain the high level picture. Let me start by considering 2 extreme cases. So let's say we're trying to prove this theorem, and let's say we want to count the number of integer points occurring in some interval I. Okay, I goes from, let's say, 0 to L. So think of I as a subinterval of 0 to n. Right? We were trying to count the number of integer points occurring in 0 to n. Let's look at the subinterval 0 to L for some parameter L less than n. Now, by shifting the picture, we can ensure that the magnitude of f throughout this interval is bounded by L. Okay, because if that's not true, then, you know, the derivative of f is small, so f doesn't change by too much in this interval. And so if you shift the picture appropriately, up or down, you can reach the point where the magnitude of f is bounded by L. Okay, so let's assume that without loss of generality. Now there are 2 extreme cases. The first case is that for some parameters t and delta, the derivatives of f are bounded for all points x in the interval. Okay, so that's the first case. All of the first dt derivatives of f are bounded for all the x in the interval. Now, really, in this part of the proof, because I'm only proving the weaker theorem, the derivatives for I bigger than d are 0. Okay, so this trivially holds. But I'm going to keep the form of this case just so that I can apply it in the more general setting later. Okay. So that's the first case. All the derivatives are small. in this sense. And the second extreme case is that this bound holds up to some number k minus 1, but when you try to look at the derivative, the kth derivative, you get that not only does the bound not hold for all x and I, in fact, for all x and I, the opposite happens. For all x and I, the kth derivative is above this threshold. Okay. So these are two extreme cases, and I want to, they're not complementary to each other because, you know, in general, it could be that for some x and I, you have the derivatives being up or down, above the threshold or below the threshold. But let's try to understand what we can say in these two cases. And let's start with the second case first because it's easier. So suppose you have that for I that's at most k minus 1, the derivatives are smaller than the threshold, and for k, it's at least the threshold, and these bounds hold throughout the interval. Then what we're going to conclude is that in this case, the length of the interval must be small. The length must be less than or equal to 2 over delta. Okay. You cannot have a function which has very small derivatives up to k minus 1 and then suddenly a large derivative everywhere. And that's just an application of Taylor's theorem. Apply Taylor's theorem by expanding f around the point 0 and then evaluate that expansion at L. You get that f of L minus f of 0 can be expressed with this formula, where here are the first few terms of the Taylor expansion, and then here's the remainder term. Okay, and the remainder term, you get equality for some zeta that's in the interval I. Okay. But now we know that this last term is large. Okay, this last term is at least contributes at least this much. So on the other hand, the magnitude of this last term can be bounded by the other terms. That's what I've done here. So when you apply the bounds we have for all of the previous terms, you get this inequality. And now you see it's a computation that this inequality implies that L times delta is at most 2, which is exactly what I claimed. Okay, so if you're in this case, the interval must be small. That's the conclusion. Now, what happens in the first case? And this is the more interesting case. This is the case where we're going to actually count the number of integer points that show up in the interval. So how are we going to do it? So I claim that if we have this bound, we have a bound on the number of, on the magnitudes of all these derivatives, we can actually control the number of integer points that show up in the interval. And to do this, we're going to ultimately appeal to Bezout's theorem. So we're going to find a polynomial that covers all of these integer points. So in order to find that polynomial, consider the following set of monomials. So consider the monomials m, which look like x to the a prime times y to the b prime, where the degree of m is between d and this parameter t. And moreover, x to the d does not divide m. Okay, so this is some set of monomials. The first observation is that there are lots of monomials. In fact, the number of monomials in this set is exactly this parameter k, which is d times t minus d plus 1. And that's a straightforward count because for every d prime that's at least d, there are exactly d monomials. They are the monomials that have total degree d prime and a prime is less than d. There are d such monomials. So the number of monomials is what I claimed. All right, so now we found this set of monomials of size k. All of the monomials have degree between d and t, and x to the d does not divide any of the monomials. Our goal is to find a g that's in the span of these monomials, that covers many integer points of the type x f of x. Okay. So suppose the integer points correspond to the inputs x1 through xr in this interval. And suppose the set of monomials is m1 through mk, then we can define a matrix M, where every entry is a valuation of one of the monomials on one of the integer points. Okay. The key lemma is that if all the parameters here. There are lots of parameters. I know we don't need to worry about the specific form, but if the parameters satisfy this inequality, then the rank of M is less than the number of monomials. Okay. And that means that there's some non-trivial linear combination of the monomials that evaluates a 0 on all of the points. Okay, so that gives you a polynomial G spanned by the monomials that covers all of the integer points. Now we want to apply Bezout's theorem. So we want to control the number of integer points. So we want to say that this polynomial is not divisible by y minus f of x. And that's a consequence of the choice of monomials that we've made. Because if you have g that's equal to y minus f of x times some other polynomial h, then consider the largest monomial in h, meaning take all of the monomials in h, order them by their degree, and then within monomials of the same degree, order them by degree in y. And take the largest monomial in this ordering. So if m prime is that monomial, then you see that m primes times x to the d occurs in this product and is not cancelled out by any other monomial. Okay. So it survives. That means it must be a monomial of g. But such a monomial cannot be a monomial in g by our choice of the set of monomials m. And Bezout's theorem says there's at most d times t such integer points. Okay, so all that's left to do in this case is to prove this key lemma, and this is where we'll use that really brilliant idea that I mentioned at the start. What we'll do to show that this matrix has rank less than k, we'll prove that every k by k minor of the matrix has 0 determinant. Every k by k minor has 0 determinant. All right, so how can we do that? So these steps of the proof involve a lot of calculations, and I'm not going to go over them very carefully, although I've written all of them down in the slides. So the first lemma says that if we have the bounds on the derivatives of f that we talked about, then we can translate them into bounds on the derivatives of the monomials. Okay, on similar bounds on the derivatives of the monomials. So if you write fj of x to be the evaluation of the jth monomial in our set on x f of x, then the derivatives of the monomial satisfy these bounds. Okay, and that's a simple application of the product rule of derivatives. So if you think about writing fj of x as a product of a bunch of x's and then a bunch of evaluations of f of x, okay, a of these and b of these, and repeatedly apply the product rule, you end up with this formula for the magnitude of this ith derivative of x. Okay, and because you know x lies in the interval 0 to n, you can get this upper bound. Okay, you can check the calculations if you want, but I'm not going to do it here. So you get an upper bound on the magnitudes of the derivatives of the fj's. That's the first lemma. A second important lemma says that for every ij there is a kappa in the interval, so that the ith derivative of fj can be expressed as a linear combination of the values of f at the first I plus 1 points, the first I plus 1 integer points. Okay, so this is some linear combination of the values of f at the first I plus 1 points, and that's equal to a derivative, an ith derivative of fj. And this lemma is very nice, and it just uses some standard ideas. So the point is that you can easily construct by interpolation a polynomial g of degree I that agrees with f on the first I plus 1 points. Okay, just interpolate to obtain a polynomial that agrees with f on the first I plus 1 points. And because this polynomial agrees with f and I plus 1 points, that means that this polynomial is 0 for I plus 1 points. And that means by Rolle's theorem, the derivative of this equation is 0 at I points. And the derivative of the derivative is 0 at I minus 1 points, and so on. So continuing in that way, you eventually get that there must be some kappa in the interval where the ith derivative of that equation is 0. And that exactly, that's what gives you this equation, because the ith derivative is just the coefficient of x, is determined by the coefficient of x in this equation. So that's what the ith derivative is here, and the left-hand side is exactly what you have here. Okay. So that's where this lemma comes from. Putting these two lemmas together, we get that we have an upper bound on the ith derivatives of fj, and they are expressed as a linear combination of the evaluations of fj on the first I plus 1 points. Okay, and that means now if you take any k by k minor a of the given matrix, and let's write the matrix B to be a matrix that has the derivatives of each fj at these points kappa ij that are given by this lemma. Then what you see, then the claim is that if the parameters we have here satisfy this equation, the determinant of this matrix must be 0. Okay, and why is that true? It's because this equation says that the matrix B can be expressed as L times A, where L is a lower triangular matrix. It's the lower triangular matrix given by this equation. And that means the determinant of B is equal to the determinant of L times the determinant of A. And we can bound both the determinant of L and the determinant of B using this inequality. That's because the determinant of L, it's lower triangular, so it's just the product of the diagonal entries, and the diagonal entries are controlled. Okay. They can be expressed like this. So here you have the nice formula that's this determinant is at least L to the minus k plus 1 choose 2. Now to bound the determinant of B, we can use the formula for calculating the determinant that uses all the permutations and taking the relevant products, just writing the determinant as a sum of products. And the lemma that we have here says that you can control that by this quantity. Okay, and when you calculate it a little bit, what you get here is an expression that looks like n to the power the sum of the degrees of all the monomials in our set. Okay, which we can compute exactly the set of monomials we have. The sum of the degrees is exactly d times, is upper bounded by d times t plus 1 choose 2. Okay. That's because every monomial of a certain degree occurs d times. Okay, so the contribution just looks like it's upper bounded by the sum of all the possible degrees. So you end up with this formula, and this has been set up so this is exactly, so it says that the determinant of A, its magnitude is the ratio of these two quantities, but that's exactly what's written here. Okay, and so that's assumed to be 1. So this number must be less than 1, but this is an integer, and if its magnitude is less than 1, it must be 0. Okay, so it must be 0. So that's the proof of the key lemma. Now let's try and put all of it together. So recall again, this is the theorem we're trying to prove. And to prove the theorem, we're going to use a recursive argument in both of the cases we just discussed. So initially, we'll set the interval I to be the entire interval, okay, of 0 through n. And we have those parameters delta k, t that we discussed before. So here's an easy lemma to prove. So it must be the case that, now remember, f is a polynomial. It's a polynomial of degree d. So if you look at its ith derivative, this is a polynomial of degree at most d. And polynomials have the feature that either they are equal to the same value in the whole interval. Okay, they could be the constant function. And if that's not the case, they can take on that value at most d times if they're degree d polynomials. Okay, so that just proves this lemma. So the lemma says that either the ith derivative is equal to the threshold we want it to be in the entire interval, or it takes on that value at most d times. So if we're in this case, you know, we don't do anything. If we're in this case and it takes on the value d times, then take all of those d times that the ith derivative hits that threshold and collect those points. Okay, those are a bunch of exceptional points. Those are the points marked in red in this picture. So we have this interval I, and there's some exceptional points, the points where the derivative is exactly equal to the threshold, but the number of those points is small. In fact, the number of such points is at most d squared times t. That's easy to calculate. And so you can partition the interval into pieces, into at most 1 plus d squared times t pieces, where in every piece, either one of the two cases we discussed holds. Okay, so in each piece, either the first case holds, all the derivatives are below the threshold, or in the second case, some number of derivatives are below the threshold, and then there's one that's above the threshold in the entire interval, in the entire part of the interval. So we can break up this big interval into smaller intervals, not too many of them, at most 1 plus d squared t of them, so that in each piece, one of the two cases holds. Okay. And that means, you know, if you're in the first case, so suppose you find some long interval where the first case applies, then pick the parameter L so that this inequality holds. This is the inequality we needed to bound the determinant. And partition this long interval into 1 plus, at most 1 plus n over L pieces of this size, of the size L. Okay. In each one of those pieces, we found a low degree polynomial that accounts for all of the integer points occurring there. And therefore, the number of integer points in each one of those pieces is bounded by d times t. Okay. On the other hand, if you have case 2 happening, meaning that one of the derivatives is large in the entire interval, then by the argument we discussed before, it means that the length of this interval, this piece, must be at most 2 over delta. Okay. The length of the interval must be 2 over delta. So the upshot is that we can bound the number of integer points using this formula. The number of integer points in an interval of length n is bounded by the total number of integer points we find from case 1, which looks like this, plus the number of integer points we get from case 2, which looks like this. Okay, in case 2, we simply recurse the argument on the smaller interval of size 2 over delta. So finally now, let me show you how to put all these calculations together. There are a lot of variables and you have to set them carefully. And I'll just give you a sketch of how to do it. So this is the kind of bound we obtained in the last slide. So it turns out a good way to set things is to set t to be d plus log n minus 1 and k to be, and this makes k to be equal to d log n. So after that setting, what you have is that the ratio of these two binomial coefficients, which show up in many of the formulas, is more or less d plus log n squared divided by d log n squared. Okay. It's that up to some lower error terms. Now, what you should do is you should set 2 over delta to be this formula, n divided by this 2d squared t times this ratio of the binomial coefficients. And you know, this 2d squared times t is the same number that's showing up here, okay, which is important. Okay, finally you need to set L so this inequality holds. Oh, there's an extra L here, which you should ignore because I've added L to this equation. But what that gives you is that n over L looks like this quantity, which essentially looks like n to the power of the ratio of these binomial coefficients times d. Okay, and that's because this dividing by k plus 1 choose 2 kills all the other terms here. All the other terms are dominated by this one. Okay, so that's something you can check. And the upshot is that you get eventually a formula of the type p of n is bounded by some polynomial in d and t times n to the power dt plus 1, you know, this ratio, plus another polynomial in d and t, and p evaluated recursively on a smaller interval. And the size of the interval here has been chosen to be so small that the win that you get from this being smaller, when you recursively run the same argument on this smaller interval, this n to this power will reduce by a significant enough factor that it will kill the contribution of this 2d squared times t term. Okay, so I've chosen the ratio that it drops by exactly so that this term here will kill this term when you evaluate p on this on the smaller interval. So the upshot is what you get is some polynomial in d and t times this times a geometric series, which now you can bound with some calculations. When you open up these things and use this estimate, you get exactly the claimed bound. Okay. All right, so that's a rough picture of how to carry out the calculations. So the end result is we get the weaker theorem that I promised. So now let's turn our attention to proving the stronger theorem and also these theorems. So the main assumption that we had here is that the derivative of f was bounded. Okay, and also in the strongest version, there's no little f at all. You just have a polynomial in both the variables. And the stronger version, you know, the picture looks quite complicated, right? So here's an example of a polynomial in two variables, and this is the set of zeros of that polynomial, and you can see that it's really crazy. It doesn't look at all like the graph of a polynomial. Okay, and we still want to control the number of integer points in this picture. The idea will be that we'll use Bezout's theorem again to find a number of exceptional points, a small number of exceptional points. Those are the red ones in this picture. And then we'll cut the picture. So we'll cut all of the places where f is 0 into segments. So you can see, you know, maybe we might have this segment, or this segment, or this segment. And for each one of those segments, we'll bound the number of integer points separately. Okay, so how can we carry out this cutting? So let's say here's you know, a simplified version of that picture. So these two curves are two. This is a set of points where the polynomial f of xy vanishes. Let's consider these four polynomials, g1 through g4. They're all the partial derivatives of f, the sum, and their difference. Okay. Now all of these partial derivatives have degree at most d minus 1, so f does not divide any of these polynomials g1 through gf. And that means that the number of common roots that f has with any of these polynomials is bounded by order d squared. Okay. So here are those common roots. Now what I want to claim is that, let's say you take a segment that looks like this. In this segment, the first thing I want to claim is that it must be the case that the gradient. First I want to say that this segment really looks like, this piece really looks like a place where you can express the set of points where f of xy is 0 in the form y equals f of x. And that's because of the implicit function theorem. You see, if you have a point like this where you have if you have any point in this picture where the gradient of f is non-zero, right? Think of f as describing the contours of a hill. These are like contour lines, right? These are points where all of those points have the same altitude. And generally, if you're in a place where the gradient is non-zero, meaning that there is a slope upwards, and this is a nice smooth function. So locally, at a place where the gradient is non-zero, it looks like a plane. Right? You're just going up. And in that case, there's only one direction you can walk in to stay at the same altitude, right? So the set of 0 points must look like really a line. Okay. If you have a place like this must be a place where the gradient is 0. Okay. That's the only way you can have sort of multiple directions you can walk in and still stay at the same altitude. Okay. And all such points are accounted for here, right? If the gradient is 0, then all of these are actually 0. All of these g's are 0. But the other thing that we have is that you can apply the implicit function theorem to all the other points, and there we get that actually the set of zeros can be described by an equation like y equals f of x. And the derivative of f, this derivative of little f, is a ratio of the partial derivatives of the big F. And the choice of these g's ensure that in between two of these exceptional points, you must have that this ratio is either bigger than 1 throughout the entire set or smaller than 1 throughout the entire set. So if this ratio is smaller than 1, we set y equals f of x, and we're now back to the old case. We're almost back to the old case because f is no longer a polynomial. It's some other smooth function. But we now at least got that y is equal to f of x, and the derivative of f is controlled. If you're in the other case, where the ratio is not bounded, it's above 1, then you set x equals f of y for some smooth function f. And again, the derivative of that function is bounded. Okay. So the upshot is, it's enough to prove this theorem under the assumption that we have a smooth function f, meaning that it's differentiable as many times as you want, such that x f of x describes this zeros of f, and also the derivative of f is bounded in the entire interval. Okay. And in that case, we need to prove the same kind of bound that we had before. And that's exactly what we'll do. And the proof looks identical to what we did before, more or less. Okay, so as before, there are two cases. Either all of the derivatives are small, or they're small up to some point, and then large. This calculation is identical to what we had before. We have to be a little bit careful about how we pick the set of monomials now. So now let x, a, y, b be the maximum monomial of f. There's no little f anymore. Okay, we just have the maximum monomial of f, and pick the set of monomials m to be those monomials of degree, just like before, which are not divisible by the maximum monomial. Okay, the size of the set of monomials is exactly the same as before. Here there's a typo. This should be a t. Okay, it's the same as before. But once again, we get the same kinds of results. This time, g cannot be expressed. You cannot have that f divides g, because if g is equal to f times h, you get a contradiction by considering the maximum monomial of h times the maximum monomial of f. Oh, it should say here that this product will be in g. Okay. The argument is the same. If you take the largest monomials in f and h, the product will be a monomial that's not cancelled by anything else, but cannot be in g. Okay, so f cannot be in divide g, and Bezout says that there are at most d times t integer roots. There are at most d times t roots, common roots of f and g. These calculations are all the same as before. Okay, it's nothing to do. The next place where there's a change in the proof is here. So previously we had we used the fact that little f is a polynomial to bound the number of roots that it has, and now we no longer have that. Now we just have that there is a polynomial f in two variables, capital F. F vanishes at the points x, f of x. And then we again want to control the number of times that the derivative of f takes on this value. Derivative of little f takes on this value. And this time we get a slightly weaker bound. We get a bound of I times d squared for the ith derivative. Okay, so that's what gives you a slightly different bound overall, but otherwise the calculations are more or less the same. So now let me turn to proving this lemma, okay, which will require a little bit of work. So here's the lemma again. So I want to show that if f is irreducible, little f is smooth, has many derivatives, and you have that f of x f is equal to 0 in the interval, then for every parameter c, the ith derivative of f is either equal to c in the whole interval or takes on that value at most id squared times. The key claim in the proof is that there's actually a polynomial hi in two variables of degree roughly I times d. Okay, its degree will be this expression, satisfying this identity. Okay, hi of xf plus the yth partial derivative of f evaluated at xf to the power 2i minus 1 times fi of x is equal to 0. So here you should be careful. What I'm writing here is take f, which is a polynomial in two variables, take its yth partial derivative. This gives you another polynomial in two variables, and then evaluate that polynomial at x f of x. That's what this identity is saying. So let's first take this identity as a given and complete the proof, and then we'll return to proving it. So given this identity, let's define g to be this polynomial in two variables. Okay. Now you see that when you plug in for y f of x, you get this identity because h evaluated x f of x is equal to minus of this the minus of this term. Okay, so plugging in f of x and substituting the value of hi x f of x gives you this identity. Okay, so whenever f of x equals c, this proves that g vanishes, which means that all of the points where that happen is a common root of f and g. Okay, so if f does not divide g, then Bezout's theorem says that there are at most id squared such roots. Now what happens if f does divide g? Well, in that case, g at x f of x is equal to 0 in the entire interval I, because f, capital F, satisfies that identity, and f divides g. And that means that either this thing is 0 or this thing is 0. Okay, so whenever this is non-zero, this must be 0. Okay, so this identity must hold whenever this is not 0. But f cannot divide the partial derivative of f. Okay, so the number of points where this is 0 is finite by Bezout's theorem. Okay, that means that fi of x must be equal to c for everywhere except for some finite number of points. But the I derivative of f is a smooth function. So you cannot have a smooth, if you have a smooth function and it's equal to c everywhere except for a finite number of points, then it just must be equal to c everywhere. Okay. And that proves the lemma. Okay, so the only thing that's left to do is to prove the claim, which also has quite a clever proof. So to prove the claim for I equals 1, you prove it just by taking the derivative of, we have the identity f x f is equal to 0 everywhere in the interval. So take the derivative of this identity and you get this expression is 0, and that's exactly the form that we wanted. Okay, this is the polynomial hi. This is the appropriate power of the partial derivative of f, and here you have the first derivative of little f. For I bigger than 1, take the previous identity and take its derivative. And when you do that, you end up with quite a complicated expression, which I've written here. Okay. And it doesn't immediately look like it's of this type for I equals 2. There are some problematic terms because, you know, I have f1 showing up here, fi minus 1 showing up, and these are problematic terms. But I'm going to get rid of them by applying induction. Okay, by applying induction. If we multiply this expression that you get here by this this quantity, then you can apply induction. For example, one copy of this times f1 can be expressed as a polynomial in x and y evaluated at f, okay, using this identity. And the reason we need 2 powers is we need to consume one of the powers to express this thing in the form xi of x, hi of xf, and we need another power to handle this part of the formula. So after we multiply this whole identity by this quantity, we recover again an identity of this type. Okay, and the degree increases exactly by 2d minus 3. You can check, and that's what gives you the bound on the degree. Okay, so that completes the proof. It's I think a really beautiful proof with some brilliant ideas using some really deep results from algebraic geometry. And I should say that in this video, like in all my videos, I talked about the ideas in this result, but not about the people who came up with these truly brilliant ideas. But if you look in the description of the video, you can find references to the people and the history of this problem. I hope you enjoyed the video.